Hey y'all, welcome back to another genetics section of the class. So today we're going to be going over another fun statistical test that a lot of people struggle on. And to be fair, a lot of people don't really struggle on the math portion behind the chi-square test. They just struggle on how to read this table in particular. And what happens is that people just memorize what the left side of the table is, what the right side of the table is. And then when you get to the exam, you're like, oh, you kind of forget which side is which. Um, so that's basically what we're going to be going over. But if you're unfamiliar with the chi-square test, all this test is basically trying to do is trying to validate a null hypothesis. So a null hypothesis, for our purposes, is basically saying that what the data that we have observed is basically equal to the data that we've thought it to be. So the observed data is essentially equal to the expected data. So that's basically what the null hypothesis is. And this test is going to be used for us to determine if we're going to reject the null hypothesis or we're going to fail to reject the null hypothesis. Or in other words, we're going to accept the null hypothesis. But nobody really says accept the null hypothesis, which is kind of really dumb in my opinion. But so what you're going to do is you're essentially going to be using these equations over here, where you have this like crazy x symbol to the second power, and that's basically what we're looking for. And whatever we get from that, whatever we get from that, we're gonna use it in this table over here. Okay. So essentially, what this is in this equation we have a sigma notation, which basically means that every time when you have an independent variable, you're gonna add them together. Okay. And then the observed minus expected is basically just the observed amount of something that you've been given minus the expected amount. Okay. And then another thing that if you look at this table you're going to realize is something called degrees of freedom. The degrees of freedom is typically written down as the 1 minus the number of independent variables, and we're going to go over some examples on that too. Okay, so that's basically a really quick rundown on chi-square and stuff like that. So let's do some genetics problems where a bunch of geneticists are always going to be using these specific types of statistical tests to determine if something is acting on a population that isn't really expected. Okay. So in the first question, what we have here is we have a situation where we have two heterozygous individuals. So we can say this is big A and little a. And we're crossing them together to get this following data set. So now we need to determine if there's a statistical difference in phenotype proportions than what was expected, okay? So now first thing you have to do is you have to determine what is the expected amount of individuals. So if you cross big A little a with big A little a, we're expecting essentially to have 1/2 chance from parent number 1 to get big A, 1/2 chance to get little a from parent number 2, from the first parent, and then the other parent has also 1/2 chance to get big A, 1/2 chance to get little a. So if you do the math and you do the product rule between these, you would have a 1/4 chance to get big A, 1/4 chance to get big A little a, 1/4 chance to get big A little a, and then 1/4 chance to get little a. Okay, so basically, since these are the same phenotypes, right? Big A, and big A, little a is the same phenotype. We're going to add these together using the sum rule. So essentially, what we're doing is we're expecting a 3-to-4 ratio to be big A whatever, and then 1/4 1/4 probability to get little a. So over here, our total if we add these together, is 57. So now what we're going to do is we're going to figure out how many people are expected to be tall. So we're going to do 0.75 multiplied by the total, which is, let's say, around, we're going to do 42.75. We're going to use the whole decimal point right here. And then for the other one, 57 multiplied by 0.25, it's 14.25. So now we have the expected and now we have the observed. So these are expected values and these are observed values. So now we can use a chi-square equation. So like I said, because we have two different independent variables, we're going to have two different fractions, okay? So let's do the tall phenotype first, where we have 45 minus 42.75 divided by 42.75, and we're going to square this as well. And then for the other phenotype, we're going to do exactly the same thing. So 12 minus 14.25 squared divided by 14.25. So let me just take a couple of minutes to multiply these together. Okay, so we got a result right here. So we got a value of 0.473. Because we have two different independent variables or two different phenotypes, our degrees of freedom is essentially just 1. So what we're going to do is we're going to go to this table, we're going to look over here at the 1 position, and we're going to find somewhere, we're going to use these values and find a value that is in between, that is close to our value, which is 0.473. So it looks something like somewhere around here and around this mark, 0.46. And then this is where basically all hell breaks loose and students don't know what, like do we reject the null hypothesis or do we fail to reject it? And you can go ahead and memorize which side of the table is which, but that's kind of useless because you will forget it on the exam. So the way how I typically do this, and if I ever forget or something like that, you can always play around with this equation, the one that I've marked over here, and you can always do some different kinds of tests so you can see what side of the table is supporting what hypothesis, okay? So what I mean by that is, let's say this is the equation, observed minus expected divided by expected. So what I tell students is, let's say our observed value is equal to 1. So let's say observed value is equal to 1. So let's say we're supporting our null hypothesis, which means that the observed is equal to our expected value. Or let's say, yeah, basically our observed value is equal to the expected value, right? So what we can say is we can say that our observed value is very, 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 very close to equal to the expected value. So same thing over here. Basically, if you do this calculation, you're going to get a number that is very, very close to 1. Okay? Now, if you do the opposite way, where we're not, where we're rejecting our null hypothesis, we're basically saying that the observed has nothing to do with the expected. It's not equal at all. So let's say our observed is still equal to 1, but our expected is equal to 0.00001, very close to 0. So what we will expect from this is that we will get something very close to 0. So what you can do here is that if we're saying that in this situation where the observed is not equal to the expected, we should expect us to be somewhere closer to the left side of the table. Okay? But then if we're saying that our observed is equal to our expected, basically we're failing to reject the null, it'll go here. So basically, in other words, if you're on the right side of the table right here, you're going to be considered fail to reject. And then if you're on the left side of the table, because we're saying that the observed is not equal to the expected, so this left side of the table, anything in between this section, we're going to be considered as rejecting the null hypothesis. So basically, in our problem, we're going to reject the null hypothesis. So something is acting on this population. So hopefully that kind of made a little bit more sense. So let's do another problem where we have this situation. We have a regular dihybrid cross. Just remember that in a dihybrid cross, we're expected to see a 9:3 or 3:1 ratio. Basically, the total here, basically we're expecting to see 9/16 of brown and yellow, 3/16 brown and green, 3/16 wrinkled and yellow, and then 1/16 wrinkled and green. So now let me do the math real quick for this. And you can do the math with me as well. So 556, we're going to multiply this by 9/16. So this is expected to be 312.75. $60.75, $56.81, 32.18. Okay, so now, like I said, we're going to have 4 different things that we're adding together, 4 different phenotypes. Our degrees of freedom, because we have 4 different phenotypes, 4 different independent variables, is equal to 3. So our chi-square value is going to be 315 minus 312.75 squared divided by 312.75 plus 108 minus 60.75 . And I am running out of space, so we're going to continue this on the bottom over here. Okay, so now let me take some time to calculate these out. So this is basically what I got. So my chi-square value was 82.016. So we're going to try to find that with 3 degrees of freedom. So we're looking over here. We're looking for somewhere in between. So we're way over here on the right side. So what we're going to do is we're going to fail to reject the null hypothesis. And we're going to say, in other words, that our expected values were basically very close to our observed values. So that's basically how you do chi-square problems for genetics. So hopefully this helped you out. But yeah, that's it.